Hello everyone, I'm Ifan. Welcome to my final project presentation, the numerical investigation of quantum tunneling by using Schrodinger equation. Now I will focus on my presentation. I will explain the purpose and the steps of this final project. First of all, for this final project, I will use the programming language Julia to simulate the behavior and states of particles and wave packets in the quantum barrier. The second is to simulate and explore the wave packets when they turn near the quantum barrier. The third is to study the relationship between them and draw pictures by adjusting the parameters of wave packets. Finally, of course, learn and be familiar with the new and powerful scientific computing language Julia. At the beginning, I'd like to talk about some basic concepts about quantum mechanics and quantum tunneling. Quantum mechanics is a kind of physics used to describe the state of motion of tiny particles. In the quantum world, there is such a magical phenomenon that when you climb a mountain, even if you don't have enough energy, you have a certain probability to turn the mountain. This phenomenon is called quantum tunneling. It is often observed in the environment around the 1 nanometer scale, such as diodes of nanochips. These are the theories supporting my final project this time. In this figure, the E means the energy of the particle, and the V means the potential voltage of the whole barrier. So when the particle turn near the barrier, just a few of them succeed, and the rest of them will be reflected. Next, I will show the derivation of the one-dimensional time-independent Schrodinger equation. Since it is one-dimensional, we are free to shift the origin of the potential energy scale, so VR equals 0. And the particle is in the area, then we can ignore VR phi. And we get the solution of the wave function phi and the energy. There is an important parameter called k. K is defined to control the odd or even parity of the wave function. You can see the following formula. If n and L equals to 1, the cosine function is the blue line, which is pi over 2. So the energy of this function is pi squared over 8, which is 1.2337 if I set m and h as 1. Next, let's see the TDSE. It is interesting if we add the variable time in Schrodinger equation. There is a video and we can see how the wave packet moves through the barrier because we have the time variable. Due to a particle is unstable in the quantum world, so we always use wave packets to describe particles. We can see the wave packet is going through the barrier, decay rapidly in the barrier and get a small transmission wave packet eventually. And most of the incident wave packet is reflected by the barrier, and that is the one-dimensional quantum tunneling by using TDSE. So how we use TDSE and TRSE in the Julia? We know the Schrodinger equation is an analytical solution. So about numerical solutions, the Schrodinger equation can be written as a differential equations like shooting method and leapfrog method, and it can be used in program language. Then I can use Julia to draw the figure like it, which is the same as the previous one I taught in TRSE. Also, I list my software and hardware, and I want to talk why I use Julia. Julia is a new and powerful language, and it has the great performance at C, and it still is simpler than MATLAB in scientific computing. It has specific vectorization that is quicker to calculate array by array. Then let's see what I have done in this project. First, in TRSE, these 4 figures show 4 different bound states of the particle in the barrier. So the red line is quantum barrier, and out of the barrier, the potential voltage is very high. In the barrier, the voltage is 0. Then I use Julia to simulate and find the energy of every bound state level. I said when the n equals 1 in the cosine-like figure is here, and the rest of them are n equals 2, 3, and 4. The energy levels can be detected by decreasing the initial energy and find the lowest level. To compare the numerical and analytical solution, I make a figure. To compare two methods, it shows that the error of two methods is smaller than 1%, which means the numerical method is great to simulate in the computer. Also, I explore if I change the outside potential voltage, what will change on the wave function. The rightward figure shows when I increase the voltage, the ground state energy is increased and then beyond 1.337, which is pi squared over 8, and keep flat over 16,000 volts. So we know the 1000 volt is the most suitable voltage to simulate the TISE. But we still get the same value, which is beyond the 1.2337. This is because the error between two methods, which is of 1%, it doesn't affect the result. Next, explore the area which is out of the barrier. The wave function will decrease rapidly out of the barrier. The decay length can be expressed as a subtraction of the x value of the first point, which is b, and the x value of the point of 37% of phi b, which is point A. Decay length can be written as xa minus xb. Why we use 37%? Because it is equal to 1 over e, which is the factor used in measuring with decay time. So it is also used for measuring decay length. So when I increase the outside potential voltage, I find the decay length will decay exponentially. Then I use MATLAB fitting tool to fit the exponential figure, which is a perfect fitting. The R square is 0.9985, the perfect R is 1. Then I talk about the results of TDSE. By modifying the parameter of values and wave packets, we can observe the different behaviors of the wave packet when turning on the barrier, and explore the relationship between them. Find when I keep the barrier width and change the barrier height, the transmission wave packet will decrease rapidly and exponentially. The reflection wave packet will increase as well. And when I keep the barrier height and change the barrier width due to some reasons, when increase the width of barrier, sometimes the wave packet in the barrier will disclose some wave and return to the previous area. You can see there is a small wave packet near the reflected wave packet, so it will affect the total height of the wave packet, and this is the reason why the result is unstable, but it becomes a flat curve eventually, so it doesn't affect the result. Next, I try to develop the quantum resonant tunneling by creating double barriers. In this figure, I set the barrier width and distance narrow, and when the transmission wave packet is generated, it will oscillate with the barrier and make a resonant wave. The height of resonant wave packet is bigger than the transmission wave packet, so the transmission packet is about 1.5, but the resonant wave packet is 4.8. Then I keep the barrier constant number, which is 2 to the power 6, and increase the k0. K0 is a parameter of the wave packet which can control the velocity and energy of the wave packet. It's the same as the k in the TISE. And I find that when the k is in the specific value, the height will increase rapidly, and in the other values, the height will keep flat. So I draw this picture. This is one of the characters of the resonant tunneling, because the area between the two barriers is like TISE. They have discrete energy levels. So when K0 reaches the level, the height of the wave packet will increase rapidly. Finally, I simulate the difference energy of levels of TISE successfully. The results are matched, the analytical results. Then I compare two numerical methods of Schrodinger equation, and their results have a perfect match. Next, I explore the decay length, which is out of the barrier, and the result has a strong agreement with the quantum theory. Next, I simulate the wave packet and make it turning the barrier successfully. find exponential and other nice relationships between measure and wave packets. Finally, I observed the resonant current successfully found when the energy of the wave packet increased, the resonant wave packet will reach the different discrete energy levels and show the result step by step. Thanks for listening my presentation. Bye bye.